on using the Desmos graphic calculator for differential calculus operations. So what I'm going to do is I'm going to open a web browser first, if I can do that. Yes, I did. Then I'm going to search for desmos.com, and on this website we have the graphing calculator option. When I click on it, I get a two-dimensional space, and here is a control bar for writing down our functions and operations. So let's just input some function here. I'm going to name it as the f of x, and it's going to be sine of x minus 2 squared plus 0.4x. And just please notice that I don't use commas for separating decimals here. I'm just using dots. If I had used the comma, it would just give me an error. It wouldn't understand what that is. So you have to use the dot operator for separating decimals. And then I'm going to put in some conditions here. Let's say that x is less than or equal to, say, 3, and it's greater than or equal to -2. Something like this. So I just sliced the graph, and according to this domain, my x's start from -2 and end at 3. This is my domain, and just looking at this function, I can just see that the smallest possible value for f of x is roughly -1.52, and the greatest possible value I can get is 2.04. So this is the range of my function. It starts from -1.53 and ends at positive 2.04. And these are my margin points, -2 and 3. I have several additional Extrema here. These are just 2 of them. These are my margin points. I don't see any other interior point where the limit is not defined. So I'll just pass on that and move on to the critical points. Here I have one, another one here, and a third one here. These are my critical points that sit on a local maximum, and these guys are my local minimas, and they are also some critical points. Please do not forget that this guy is also a local minimum point, but it's not a critical point, because I cannot approach -2 from the left. Thus, the limit is not defined. Thus, the derivative at this point is not defined. Similarly, this is another extremum point. This is a local max. And again, this is not a critical point because I cannot approach 3 from the right. But because of that the limit is not defined, but still this is an extremum point, a local maximum point. Other than that, I can just compute the first order derivative function for f of x. I can just write f prime of x. To get this prime symbol, I just used shift +2 on my keyboard. And this shift +2 just gave me this blue weird function, which actually is the derivative of f. And now I can just input some other version of it, and I can just say that f of x is just greater than or equal to 0. This green shaded regions on my red curve, these green shaded parts are the increasing intervals of my function, and similarly I can just get, I'm sorry, I'm just trying something here, f prime of x, yeah, f prime of x, I'm just trying to find the red shade to fit in the situation better. So now I'm going to just find the regions where this red curve, where my f function is decreasing. So within this red shaded regions, f of x has a negative first order derivative value, then the function is decreasing within these intervals. What else? I can also find the concave and convex regions of f by just computing the second order derivative. So this, again, I have a blue curve which is a little bit more weirder now. Let me just turn off in the other part. So this is the second order derivative function, which is a little bit more radical than the first order derivative, but I just don't care about the values for now. I will just concentrate on the positive second order derivative information regions and the negative second order derivative information regions of f of x. So I'll just say that f of x is greater than or equal to 0. And please notice that within this green regions, I can just observe that f of x just behaves like a ball. It is curved upwards. So this is the concave regions of f of x. And I can also just find the second order derivative information where the second order derivative is negative. And here I can just see the purple shaded regions, and within those regions f of x just resembles an entrance of a cave. So these are the concave regions of f. And other than that, for just computing the values of derivatives, I can just use this. Let's say that g of x is tangent of x, and I will just try to compute h of x, which actually is f of x times g of x. I use the star symbol on the keypad part of my keyboard for the multiplication operation. It is just transferred here as a dot product. And now I have the f of x times g of x here, which is a little bit weird function, but I don't care about it. Now I would like to find the first order derivative information for h of x, and that should be the blue curve. And I would like to evaluate this function at x is equal to, say, 1. And this time I don't get a sketch. Instead, I get the result of my operation. H of x differentiated with respect to x, evaluated at x is equal to 1, is 0. or I can just put in some other value. I can just try pi, and please notice that pi should be here or somewhere, just a little bit further than 3, where f is not defined. Thus, h of pi differentiated, sorry, h of x differentiated and evaluated at pi is not defined. Or I can just get pi minus 1. This is again 0. Or pi minus 2, which is again 0. And pi minus 4, which is again 0. So that's how you find the first order derivative information. And for the second order derivative information, you just have a better shortcut here. I can just say that h double prime of 2 is roughly negative 20. So this is how you use the Desmos graphic calculator for derivative operations, sketching functions, just drawing out intuitions from the geometric information you just get from the sketches, and so on. And that's it.